Hi everyone! We introduce score difficulty classification as a subtask of music information retrieval and music education technologies for personalized curriculum generation and score retrieval. We introduce a novel dataset for our task, Mikrokosmos-difficulty. As part of our methodology, we propose piano technique feature representations based on different piano fingering algorithms. We use these features as input for two proposed methods. The models are interpretable and are also able of generating difficulty feedback both locally on short-term segments and globally for whole pieces. Classification of music corpora is a well-studied problem. There are big collection of scores available on internet. However, they are structured in categories not totally useful for musicians. That is said, if you cannot play the score, it is not important the composer or style. The diversity on piano repertoire is limited. For example, most of students finish playing the same classical sonatas composed by Haydn, Mozart, or Beethoven, having hundreds of sonatas composed by many other composers. In a paradigm shift, music may be classified from the point of view of the performer, by focusing on the required performance skills. But well, yet it is true, difficulty is a very subjective term. However, publishers, examination boards, and online repositories classify scores based on performance difficulty. In addition, the difficulty have multiple dimensions. For example, expressivity, rhythm, sound, or technique. And previously, there wasn't a public dataset for the task. Although there isn't many previous proposals, Nakamura et al. Outstands. It uses the transitions probabilities of an automatic piano fingering hidden Markov model, but the proposal it is not evaluating difficulty in a proper dataset. Nakamura et al. Use the features for making score reductions. Béla Bartók Mikrokosmos is a collection of 153 piano pieces composed in a 20th century music language. We propose the Mikrokosmos-difficulty dataset based on a subset of 146 pieces from the Mikrokosmos collection, discarding the 7 pieces composed for four-hand performance. We group the pieces on 3 levels of difficulty according to the classification in the original editions. Correspondingly, the beginner level contains the pieces from 1 to 66, and here we have a little example. The moderate level contains the pieces from 67 to 121, and here we have a little excerpt. The professional level contains the pieces from 122 to the end, and here we have another excerpt. Moreover, we use also the ranking provided by the modern editions of Henle Verlag publisher. The conversion to machine-readable symbolic representations in Music XML was done semi-automatically, using a commercial optical music recognition software and manual corrections. In the present research, we explore features related to the piano playing technique for score difficulty analysis. In the first years, pianists learn to move fingers and hands across the keyboard. However, finger and hand movements are not usually indicated on scores as clearly as other technical elements. Pianists must develop their piano fingering ability, that is said determine the order of their fingers to play the piano keys. The excerpt usually is not accompanied by finger numbers, and each pianist has to define the best finger combinations in order to play the score, moving the hands and fingers. Therefore, we use piano fingering as a proxy of piano technique, a fundamental skill in piano performance. Previous literature proposes several algorithms for piano fingering. We select two proposals. The first one is data-driven, and the latter is based in expert hard-coded knowledge. On the one hand, the hidden Markov model fingering models proposed by Nakamura et al. Have been previously used to automatically create score reductions, indicating that can be very useful in our task. The rationale for this proposal is that piano fingerings, which occur less often, lead to increased difficulty. Therefore, we can use the transition states probabilities of the hidden Markov models for feeding machine learning algorithms. On the other hand, Piano Player is a local search algorithm grounded in dynamic programming and combinatorial optimization. It computes which finger is playing each note by considering the following 9 notes and the previous positions of the fingers. Piano Player carries out the optimization according to hard-coded constraints and a cost function related to the finger velocity. We present 5 piano technique-based feature representations to analyze the performance difficulty and an additional baseline using solely the notes. Automatic piano fingering systems aim to describe the movements of hands and fingers on the piano departing from the score. This task is related to piano technique and a proxy to modeling the difficulty of playing a score. Towards modeling difficulty, we derive piano technique features from 2 piano fingering approaches. From the cost function of Piano Player, we derive 2 features associated with each one: the finger which plays the note, and PF, and the velocity associated with the finger, P sub P. In order to reduce the size of the matrix and the computational complexity, we do not consider the note duration. In the figure, we present an example of how these matrices are formed. In contrast to Piano Player, which has hard-coded rules, Nakamura hidden Markov models learn implicitly the transition probabilities that model finger movements. We use the transition probability given by the hidden Markov model to derive 2 features for a given note: the finger which plays the note, N sub F, and the transition probability associated to the note, N sub P. We propose a 2-step classification method, XGBoost, to classify the score into the 3 difficulty classes using a decision tree classifier to local filter extraction. Since this method works only on fixed size inputs, we split the input filter matrices into windows of size 9, the same context as Piano Player. Next, the predictions corresponding to each segment are averaged across the whole score to obtain a global difficulty. Note that besides being interpretable, this method is more robust to noisy levels. In our case, we deal with a weakly supervised scenario because we have annotations only for the whole piece, and not for each segment. Moreover, the difficulty of the segments may vary across a piece. The other method, DeepGRU, is a GRU network with attention mechanism. We modify an existing architecture used in multivariate time series classification, DeepGRU. The model lies in a set of GRU, 2 fully connected layers and a global attention model. The final 2 fully connected layers, using ReLU activations, take the output of the attention module and use a softmax classifier to create the probability distribution of the class levels. The GRU's stack layers are able to model the time dependencies, while the attention mechanism selectively attends to specific note onsets, which are more important in the difficulty decision. We use the attention layer to visualize and understand the important notes. We evaluate the classification balance accuracy of the machine learning models XGBoost and DeepGRU, train it with the 5 proposed features on the Mikrokosmos-difficulty dataset. Towards assessing the impact of weak levels, we compare the 2-step classification, XGBoost average, with a single-step classification, where the predictions are not averaged across all segments, XGBoost window. In addition, we rank the scores using the output probability of the classifiers. The ranking is calculated by multiplying each class probability by their class number in the last layer. We then compare this ranking with the original one proposed by Bartók and the one by the publisher Henle using Spearman's rank correlation. In both classification methods, the 80% of data is used for training and 20% for testing. We repeat the experiments for 50 different initial random seeds, which control the initialization of the machine learning models and the train and test splits. We report means and standard deviations for the considered metrics across the 50 seeds. The results have to be interpreted considering the large standard deviations across the 50 seeds. We observe that XGBoost average yields better results than XGBoost windows. Therefore, averaging the results across the whole piece is better than considering standalone segments. We see that using transition probabilities and velocity information increases the performance compared to using the fingers only. Comparing the two finger modeling methods, we see that piano player fingerings perform better than the Nakamura fingerings. The importance of finger modeling in piano difficulty analysis may be seen in the drastic improvement for the deep group case, where all the fingering strategies improve the classification accuracy by a large margin compared to features generated directly from the baseline. The ranking performance using Bartók and Henle difficulty rankings are shown in the table below. Even though the models are trained using only 3 class labels, the difficulty rankings we derive evaluated against the rankings provided by the composer Bartók and the publisher Henle achieve high correlation. As a practical application to music learning, giving feedback related to the local difficulty of a piece allows students and teachers to focus and improve on the most difficult passages. We share a visualization tool to explore the Mikrokosmos dataset based on the proposed feedback. This feedback is an indicator of the local difficulty corresponding to each node. In the case of XGBoost, the green nodes correspond to the level 0. The yellow ones to the moderate level and the red nodes are the most difficult ones. However, most of piano pieces of Mikrokosmos have a similar difficulty because are composed exploiting some technical pattern. Also, we admit there are noise in the feedback. However, in other pieces, we can affirm that we can see differences in the difficulty that have sense. This method grounds on the weights of the attention layer in the deep group model. Attention tells us the nodes on which the model is focusing. The darker blue indicates more attention. The most interesting aspect of the present feedback is dealing with repetitions that occur in the short term. The attention reasoning is similar to how music students should study. When dealing with two similar patterns, students should study the first one very well and repeat the second one by imitating the first one. However, in other pieces, the method pays attention in every place, without give a clear feedback. In this work, we propose a methodology to classify piano scores based on piano technique features. Namely, we derive piano fingering features from two approaches and a simple baseline based on using the notes in the score. Towards training and testing machine learning methods for this task, we distributed the Mikrokosmos-difficulty dataset. We evaluated two interpretable machine learning methods on the proposed dataset to show that piano technique features are good predictors for the difficulty of performing a piece. In addition to the openly available source code, models, and data, we also provide an online demo which visualizes the segmental difficulty, which is crucial in educational feedback. We acknowledge that the small size of the dataset may lead to overfitting biases and large standard deviations for the bootstrapped experiments. In future, we plan to extend this work with larger score dataset, allowing research on the multiple dimensions of piano fingering. Thank you so much to everybody.